Hello again. It's working now. Yeah. Hello again to everybody, and it's just great to be back here in Prague. After 2002, we thought that Zdeněk deserved another chance. So when EME 2020 came along, we said, yeah, we're coming, and then COVID, but hey, third time lucky, we're here. So can I move on to introduce a very old friend of these conventions, which is Paul, W1GHZ, and to talk about a new departure, design optimization of Cassegrain antennas. Thank you, Paul.
Thank you, Ian. Good morning, all. Or moin moin, as my daughter in Hamburg says. Well, I'll start by telling a little story off topic. Some of you went to the planetarium the other night and saw the presentation about the Voyager. Well, 50 years ago, more or less, I was working at Microwave Semiconductor, and we were making the transistors for the S-band power amplifiers. Intense quality control, ever wafer scanning electron microscope inspection. And the Voyagers had 2 solid-state amplifiers and 2 TWTs. Well, the solid-state amplifiers failed before they got to Mars, and they're still going with TWTs. I hope things have improved in the last 50 years. Okay, anyway, I'm going to try and tell you about Cassegrain antennas. If I can get the right button here. Yes. I think that's OH2, I've forgotten what it's called, but that's a picture of a nice one. And we'll remember Cassegrain has a subreflector and a feed horn. And and of course, it's a very old design. The museum in Dresden had this nice Cassegrain telescope. And you can even make them pretty. But the idea is to make it shorter and get the eyepiece or feed where it's convenient. That's one of the advantages. So, today we'll talk about the geometry and system design. And then, so this is just not theory, examples, results. You can even make them pretty. That's what we want, results. But the idea is to make it shorter and take what you got. Eyepiece or feed, take what you got, get it on the air. That's okay. So why a Cassegrain antenna? Well, at the higher microwave frequencies, a feed line is a disaster. Even waveguide above 10 gigahertz is lossy. You don't want to run a big piece of waveguide out to the feed. And you can put the equipment at the focus, but most of the dishes I've seen, or many, we don't have all the concrete like one KIR that could move a building. If you start adding more equipment at the focus, like a 100-pound TWT, all of a sudden you're way out of balance, and I've been present at least one dish breaking the elevation gear, and it's a big crash. It's very bad for the performance. So we can move the equipment behind the dish and get it better balanced. That helps. And mainly, we get the lower noise, higher G over T. Good for EME and radio astronomy. And finally, we can actually illuminate deep dishes, which I don't know about around here, but they seem to be often available in the U.S. that nobody wants to use them. So, higher G over T. All the spillover from the feed horn just goes up into space and contributes very little. With a really deep dish, even at a fairly high angle, you've shielded from the ground by the reflector. So that could be an advantage. Problems, oops, whatever I hit. Yes. Need a big dish to be effective. The original paper about Cassegrain antennas suggested that you need about 50 wavelengths to be really effective and about a 20 wavelength subreflector before you get to equivalent or better performance in a prime feed. Of course, if you add a few dB of feed line loss to that, it moves the equation pretty quickly. Since loss equals noise sphere equals lots of G over T. Yeah. Hard part is the hyperbolic subreflector. It used to be very difficult to make. A friend of mine, W1RIL, now a silent key, actually made one on a manual lathe just by cutting diameters for hours. Today, we have CNC machinery, computer numerically controlled, and 3D printing. And the final problem for some is the design is a little more complex than dividing the diameter by the F over D and figuring out where the feed goes. So, next slide. So, we can start out with a simple flat subreflector like these. Who's the company over here makes these little white dishes? Anyway, you put it here, you slide this around and hope it's peaked, usually on too short an antenna range, and you have feed line loss as well, and a very poor feed because it's just an open waveguide. But you make contacts, that's the important part, so. All right, and here, KJ1T, who originally Dutch, so some of you might know Henry, was working 148 kilometers on 78 gigahertz, so that's not too bad. Let's see, next slide. Okay, so hyperbola. You all remember from geometry 50 years ago that hyperbola is a conic section where you slice through two cones and you get two matching curves. And as you move this sheet, you get many different curvatures. So a parabola is one dimension. All parabolas are the same curve. Hyperbolas have two variables, so there are many possible curves. Okay, but the key point is if you start at one focus and reflect from the other curve, it looks to the RF or light that it came from the second focus, which is going to be the prime focus to the dish. Right. So, next slide. Yes. And again, feed point at one focus of the one curve and the prime focus to the dish at the focus of the second curve. And this curve went away. And this, the subreflector, reflects off the dish and comes out parallel just like we want, right? So, if I am talking too fast or not loud enough, yell. Yes. What I just said. Start at one focus, reflect, appears to come from the second focus and from the prime focus, and reflects into a beam, if everything is right. So, what do we need to work out? Feed horn location, where would that be? Well, we decide where it wants to be. Subreflector size, and then we calculate the curve, get the parameters, and then we calculate the points on the curve and put them into the CNC machine or the 3D printer. So, feed horn location. Yes, we want the edge illumination to be 10 or 12 dB down, excuse me, here and here, so we know the angle of radiation of the feed horn, and if it's wide, we can be close to the subreflector, but if we want it further back, we have to get a bigger subreflector for that same angle, right? So, so here's our example with a 20 wavelength subreflector and a 50 wavelength dish. That's what we need to be a good performance. And notice we've blocked 40% of the diameter, but 0.4 squared is still 16%. So that's actually not terrible. Since we typically estimate with a prime focus, we lose 15% anyway, so that's. Also, we can, instead of using the wide angle feed, we can use a narrower one and get a smaller subreflector for the same positioning. Now, I suspect all the 2-meter guys have already left because nobody has a 50 wavelength reflector at 2 meters, except maybe Jan. Okay, and for deep dishes, oops, one of those, we can actually take a feed that's for a reasonably good feed for a less deep dish and reflect it out to the edge and feed a 0.25 wavelength, 0.25 F over D dish. And efficiently, and it has that advantage that way out here has to be tilted very low before you actually see ground noise. So deep dish actually has an advantage. Feed corn can even be behind the dish if we have a narrow enough feed angle. So, and you'll see where this comes in one of the examples. Okay, so design procedure. Always start with dish F over D and decide where we want the feed horn. And then we work out the feed horn radiation angle. So not playing with F over D, we actually have those numbers that for any feed that I or the next speaker or anyone else has calculated, you have every degree all the way around. And then we calculate the subreflector size, and when it's too big, we iterate until we find a compromise. And then we calculate the parameters and generate the curve. So after you do one by hand, that's not much fun. But I made a little MATLAB routine that does all these and allows for a quick iteration until I get where I want it. And since it's a computer, we generate the code right off the program to run this CNC lathe or a 3D printer. That's just a matter of getting it in the right format, and away it goes. And I wrote a Perl script to make sketches so you can see how it looks. You know, a bunch of numbers never feels good. And a spreadsheet I made 2004, I talked about Casagreens, and that's been updated a little. Let's see. So, and that original spreadsheet, I got hung up with space attenuation, and that doesn't matter if you know your actual pattern and your actual performance of the feed. So we just machine it on a CNC lathe. You just have it cut all the little diameters all the way out, every tenth of a millimeter of depth, what I thought was probably close enough. And then take one final cut that makes a smooth curve. And all the operator has to do is brush away some chips and take pictures. Of course, the first time you run it, you keep your hand on the red button, because if you've ever run one, the one I use, the motions are hydraulically controlled, and if you get it wrong, it'll go right through the wall. Or at least break a few expensive tools. Yes. So, yeah, the 2004 spreadsheet, the parameter was equal to fraction and blockage loss. That's a good compromise for large dishes. But for amateur dishes, we'd like to get the subreflector at least 10 wavelengths, so it actually starts to look like a optical approximation. And as I said, it was compensating for space attenuation, but with good feed simulation, we don't worry about that anymore. So, let's look at some working examples. Most of these are at higher microwave frequencies than anybody but Manfred and Zdenek uses. So think of them as scale models. But to measure performance, I don't know. So we use a long antenna range, find the maximum signal, and then move the subreflector out of the beam. We know the gain of the feed horn. We know the difference. So we can actually measure the dish performance based on the feed horn performance. Anyone have a problem with that? Okay, good. Wrong one. Okay, so first example is the 122 gigahertz project by our Australian friends, and a little bitty dish, 123 wavelengths in diameter, 15.5 wavelengths subreflector, carefully chosen because that's the size of aluminum rod I had. And the dish is an F over D or 0.25. And the feed horn is a large W2 IMU feed, a 1.8 wavelength diameter, easy to build with available tooling, with a slight compromise in the flare angle, which gives us this slightly larger rear lobe and makes about a 1% difference in dish efficiency. So I figured that was a reasonable compromise. And there's the dish. 300 millimeters, 120 wavelengths. The machine subreflector right there. Feed horn there. And this model was built by W1FKF. And notice this dish is nearly optical. It's a very shiny surface. So You can tell just by looking that it's very accurate. It does have a downside, which we'll see soon. There it is. This B2UG made a 3D printed mount for the subreflector, but they both used subreflector side machine, which are at this size pretty easy. And Renee measured roughly 50% efficiency at 122 gigahertz. So for a 30 € dish, that's probably not bad, right? Second one, mine, 48 wavelength diameter, 12 wavelength subreflector. This is a very flat dish, F over D 0.6 at 47 gigahertz. Okay, and again, back one. So, as you can see, it's very narrow beam and still reflects. What happened was where are we going? Got a transverter from Michael, made 2 horns that would just barely fit on it, and went out and made some contacts, but this was the best DX I got with very weak signals, so figured we needed more. Okay. And that's the pattern of the horn. You see, very sharp angle. And again, CNC machining, no trouble. And I thought about a waveguide switch, and here's waveguide spaghetti by Ray, custom bent waveguide. And there's probably some loss in these, I imagine, a loss in the switch, though making accurate measurements in waveguide at 47 gigahertz is, I haven't been able to do it successfully yet. So I said, instead of bending the waveguide, why not match it to the transverter spacing and make a 3-port waveguide? Just machine the waveguide right into a block and a rotating plate. And, pardon? 5 minutes. We'll get there. Yep, we'll make it. So before making all the mechanism, I just put it together and tested it. It had about 2 dB loss, and it's heavy and would be hanging right off the feed. So not good. So instead, I said, oops, come on. Let's put the feed behind the dish, put a subreflector out here, and move the TR switch with no loss on a linear bearing. Just switch from transmit to receive by moving it sideways. Now, Manfred, you were trying to figure out how to have a feed for transmit and receive on the same thing. On an offset dish, you could do this, just slide it back and forth. All right. So, feed horns about 23 dBi. The dish adds 18 to 19 dB, which comes out to about 50% efficiency again. I'm happy with that performance, knowing that I have that performance, instead of knowing that the dish has a very sharp beam. All dishes have sharp beams, no matter what you put in front of them. All right. So, again. Okay, next one, I'm working on 10 gig EME. I have a very nice 1.2 meter dish. And figured a 7 wavelength subreflector is about as good as I can, is as big as I can make with the 3D printer I have available. So That's the constraint today. Maybe we can work around it. F over D, and done the numbers, but not tested that yet. Fourth one is 96 wavelength diameter and a 20 wavelength subreflector with another Edmund dish. Again, very shiny, 47 gigahertz. Here's the 4-inch, so that's a 100 millimeter subreflector on the lathe. So, and Renee V2UG and I are working on this, and the plan was to compare machine subreflector with the 3D printed. Here they are, foil on the 3D printer, metal. Now, I remember I said this is very shiny. Renee tested this one with a 3D printed feed horn, pointed it at the sun, and guess what happened? Yes, on a 600 millimeter dish, you're getting about a quarter of a kilowatt of solar energy on the feed. And you can see the profile of the subreflector. Final example, pair approached me about making a hyperbolic a subreflector for DL0 SHF at 24 or 47 gigs. With that 3-meter dish, I can't imagine pointing that accurately at the moon, but some people are better at mechanics than I am. And so here's the, with the same calculation with the higher gain feed that I used on my dish. And, but it doesn't make it easier to point. But, oh, let's go back to the last two. So, for the same dish, we could use a wider feed and have the feed horn out here, maybe put the equipment right in here instead of having it behind the dish, I don't know. Or we can move it back and shorten the waveguide, whatever works. But the point is, by picking the right feed horn, we can put it anywhere we want. Okay, so, summary. We've demonstrated that we can actually make a Cassegrain with decent performance, has advantages for large dishes, deep dishes. We can reduce or eliminate feed line loss at microwaves, get the switch out of there if you really want. And it is today within amateur fabrication capabilities, which it wasn't until very recently, except for a few people. And I can provide the design procedure tools, and I'll clean up the software and put some comments in it. And, and I think I'm right on time, right? Okay, so let's.
Thank you, Paul. Questions, please.
And there, 47 gigahertz, 148 kilometers, 5.9 SSB.
Questions for Paul?
Can I ask you what aperture efficiency did you achieve at the 4.7 times lambda on 10 gigahertz dish?
What aperture?
Aperture efficiency.
Aperture efficiency.
I haven't built that yet. That's current project. Oh, sorry. So the question was, what efficiency have I achieved on the 10 gigahertz example? And the answer is, I'm still building that, so I don't have an answer yet. But
Good answer. But please, second question. What do you mean about the dual optics offset antenna with the Gregorian second refractor?
So you're asking about an offset Cassegrain or Gregorian. Just much more complicated geometry and even worse machining.
Okay.
Unless you were going to make 8 of them and you'd cut a huge subreflector and slice them up.
It will be necessary to make it hyperbolic offset.
Other questions?
Any other question? Charlie.
You referred briefly to the accuracy of machining. Does the hyperbolic reflector need to have a higher tolerance of accuracy compared to the dish surface, given that it's kind of multiplying the profile of the dish?
Okay, the question is, does the hyperbola need a higher accuracy than the dish surface? And I believe the answer is yes. The other point I somehow left out is that the critical dimension is where the subreflector is. The distance from there to the feed horn is less critical because the optical magnification. And in my 47 gigahertz, I put a adjusting screw in, and it was less than 1 millimeter difference between the calculation and measurement point, and that's probably due to the dish accuracy.
As we know, the accuracy of the dish has to be 0.1 lambda for the surface of the antenna, so that the hyperbolic will be a little bit better. So, okay.
Yes.
Okay, any other question? No one. Ingolf.
Well, okay. Yep. And again, the next speaker really needs no introduction. Ingolf has, like Paul, been publishing his results between conferences, and so what is new now?
Thank you. Finally, we are here after 2 long years of waiting. Good. The last conference we had 218. Yes, but since 2020, waiting for this conference. And good to see you all here. And hello to everyone on the webcast as well. Anything will give you a signal, even an open waveguide. But this is all about optimization and finding and get the most out of your investment in dish and feed. And this is not a game of rule of thumb. This is all about optimization. So first, we will have some background and how to set your goals. I will touch upon feed properties and terminology. We will discuss the efficiency and G over T plots. We will look at some demonstration cases, and I will present a how-to step-by-step procedure. I will touch upon combinations you should avoid, and at the end I will conclude it all. This is and has been a well-discussed subject on the reflectors. And there are many claims there, maybe adding to the confusion of many. I will try to reduce this confusion and bring some clarity. Parts might be a recap for some of you, but I hope that everyone will find something new in here. And maybe I will kill some myths that are flying around. And finally, I will present a method to choose the proper feed. So first of all, what is your goal? Do we want to optimize for RX performance or for TX performance, or maybe a compromise? You can always increase your TX power, but how do you get rid of the noise that has sneaked into your system? And the answer is you can't. And this is even more true today, as previous speakers have been touching upon, with the very good LNAs we have today. We really can, in order to take advantage of these LNAs, we need to be careful and reduce the noise from the antenna as well. So in the next few slides, I will discuss some of these terms and definitions that are good to have a brief understanding about. First of all, antenna area. You recognize it from the radar equation, the RX part of the radar equation. And for an isotropic antenna, it's lambda square over 4 pi, and that's for 0 dBi. And for an arbitrary radiator, you just multiply by the directivity in linear terms. A larger antenna area goes with a larger physical area, but they are not the same. And the larger antenna area gives a larger directivity, and that's what you need when you feed a dish with a large F over D. And the antenna area can be increased by increasing the size in any of the 3 dimensions. And this is a fundamental property that you can't fool yourself around. Also, we need to distinguish between directivity and gain. And the directivity is only dependent on the antenna area, and the gain incorporates any losses. So to get the gain, you just multiply the directivity with the efficiency. And we will use directivity in this presentation and handle all the losses separately. In order to get good efficiency of a dish, you need to be in the far field of the feed. And the far field definition that we will use here is 2d squared over lambda, and that will give a phase error over the aperture of 22.5 degrees. And if you have a more stringent 4d squared over lambda, it will go down to 11 degrees maximum phase error over the aperture. The far field distance for a patch feed on 1296 is roughly 0.5 meter. The feed is illuminating the dish and exciting a near field, and that is parallel rays, as we have seen in the previous presentations as well. This near field will emerge into a far field within the far field distance of the dish. And now you have a plane wavefront. And for a 6-meter dish on 1296, the far field distance is roughly 300 meters. And by the way, for IMU feed, a dual mode IMU feed, the far field distance is 0.9 meters roughly. And here there are different definitions of the far field. But, oops. No. Ah, there it is. Ah, fine. So the red curve is the 2D square over lambda, and that is the one that we will use here. But all of these definitions should be fulfilled if you want to be in the far field. And aperture efficiency is built up of different losses. Of course, you want to illuminate the dish surface in the best possible way. That's why we use Kumar feeds with their typical radiation pattern. And as we have heard before here, you want to reduce the spillover loss and the feed blockage. And of course, you need to have a low phase error and a low cross-polar loss across the full dish surface. And then, of course, we would like to reduce the resistive losses as much as possible. And a good feed design will address all of the 6 first here. The 2 last ones are not feed related. These are the equations that describes the 2 most common waveguides and waveguide modes. The TE10 for a rectangular waveguide and the TE11 mode for the circular waveguide. And for a circular waveguide, you can demonstrate that in this graph. We have, this is for 1296, we have the circular waveguide diameter on the x-axis, and here is the lambda guide, the guide wavelength on this axis, and the blue curve here is the guide wavelength, and you can see that the guide wavelength increases rapidly when you're approaching the cutoff of the waveguide. These 2 red lines are 2 common circular waveguide dimensions, 0.71 lambda and 0.795 lambda. So you're at this end, you're limited by the cutoff and that the guide wavelength increases rapidly. And at this upper end, you're limited by the next mode emerging into the waveguide out of control, and you don't want that. And as you can see from this guide wavelength here, that if you tamper with the dimensions, things are changing quite rapidly, and you are on your own unless you know how to simulate and measure what you actually have been doing. And the scaling from one band to another is not a good idea either, because you will not have an optimized feed. You will get something that radiates, but it will not be optimized. And the next upper modes emerging here can be controlled by design, and then you get a dual mode feed that has certain advantages for feeding a large FOD dish. So what is then a good feed? Well, first of all, it needs to be well characterized, measured or simulated, but you should know what you're getting. Otherwise, it's impossible to optimize your system. And of course, the beam width should be suitable for your FOD and should be equal in the E and H plane out to the dish edge. low phase error across the aperture, of course, good cross-polar reaction, and that is the same as the axial ratio for circular polarized feeds. Also, a good front-to-back ratio is what you want. And as an example, if you're down to 10 dB front-to-back ratio of your feed, you actually lose half a dB of power that won't reach your dish surface. And you don't want that. And of course, there should be low ohmic losses as well. The G over T, as we have been discussing before here, is a very efficient and powerful tool for optimize for RX performance. And you have to be careful on what temperature you're using for these calculations. Is it the antenna only, or anything, all the antenna, complete receiver, and the environment, or anything in between? That will give completely different results and answers. So you need to know what you're using, data you're using for these calculations. And Paul, W1GHZ, has made a program, developed a program called FeedGT that produces efficiency and G over T plots from feed radiation pattern data. And using FeedGT, we will examine a few typical and interesting cases. So this is the plot that the FeedGT produces. And you should be able to read what kind of feed it is, the top headline. And all this data is based upon feed radiation pattern data, both in the cardinal cuts as well as in the diagonal cuts, and both copolar and cross-polar. All of it is important if you want to optimize for performance. So on the x-axis, we have the dish F over D. On the left y-axis, we have the dish efficiency scale for the red curve. On the right y-axis, we have the G over T scale. And on top of this pattern, we have the feed diameter and the dish diameter used for the calculations. And in the lower right corner, we have these temperature data that we are using. T-sky, T-ground, and T-receiver. And in this example, T-receiver is set to 0 Kelvin, and that is not a realistic case, of course. And you should never, ever be on the right side of the efficiency curve, because that is pure loss. It's pure loss, everything. You're getting more noise into your receiver, and you are on the downward slope of the efficiency. So never on the right side of the efficiency curve with your feed of your F over D. So we have 3 demonstration cases here, 1 for 1296 and 2 for 10 gigahertz. But they are in principle is applicable on any band, of course. Here on the left side, we have 0 Kelvin receiver temperature. That's not realistic, and you can see that the G over T curve is to the far left here, and you can't even see the peak. Going to the right plot, this is for 1296, this example. We have set a receiver temperature of 45 Kelvin, and still you're on the left side of the peak efficiency. But now you can see the peak of the G over T curve. So for optimum receiver performance, you want to be in this area, even though that you have slightly less efficiency, you will get a better receive performance. And if you have a lower receiver temperature, total receiver temperature than 45 K, you can be further to the left. But you can see also that it goes from 24 dB G over T down to around 17 dB of G over T as you have added more noise into your calculations. For 3 centimeters, you see the same. Receiver temperature 0 Kelvin, the G over T is large and to the left of the efficiency peak. Going for 75 Kelvin for 10 gigahertz receiver temperature. Maybe a little bit high for some of you, but maybe realistic for many systems. You're still on the left side of the peak efficiency. So here, being here, you get the optimum RX performance. So you want to have a feed that comes, or a dish F over D that comes in this region for this example of feed. And this is a dual mode feed for 10 gigahertz. A more realistic 10 gigahertz example, when you have 75 Kelvin receiver temperature and have added moon noise as well. And for this example, we have a 2.6 meter dish. That means that you're illuminating the moon and cold sky as well. So I have guesstimated the T-sky temperature to 95 Kelvin, and that is sky background plus the moon temperature for integral over that area. And as you can see, the G over T curve has moved further to the right and approaching the peak efficiency, and it's slightly wider as well. But this is in this area you want to have your F over D for optimum RX performance. But it will change with the noise that you actually have in your system, the receiver noise and the sky noise, including moon noise. And there are more comparison plots in the appendix of this presentation. Between G over T and noise temperature. So when you want to determine what feed would be the optimum for your desire, you have to decide what you want to optimize for. Set your goal. Do you want to optimize for RX performance or for TX performance. Of course, you determine your dish F over D, so you know what to compare for. And you should look for feeds with well-documented performance, like feed GT curve, for instance, where you can see what you will get. And if the designer cannot provide that, you don't know what you will get. And obviously, the designer does not know that either. Then you can do the previously described analysis with respect to your requirements and make your choice and put the feed into your dish. And then you can optimize the feed position, because in most cases the dish surface is not known well enough, so you just place it, but move it back and forth, measuring cold sky to sun, and make a curve, and then you interpolate, as Mirek said, and you will find the correct position for your feed. And that should be done in one session, so you have the same solar noise, so it doesn't change in between. Then you can check your system for key parameters, like cool sky to ground, moon noise if applicable, and cool sky to ground, and compare to EME calc. There are some combinations that are more difficult and you may want to avoid. And that would be a small, say 2 meter and less TVRO dish on 1296 that probably has F over D larger than 0.6, and you will probably suffer from blocking. And if you have a feed that is proper for this F over D, and you will probably not be in the far field of the dish, and that will give you phase error and other errors that you will not illuminate your surface in the best possible way. And of course, using an incorrect wide-angle feed, you will have overly illuminate this surface and get a lot of noise into it. And the very deep dishes are difficult to feed in an efficient way. But in the special cases, low noise applications, oops. Yeah. It may be an asset with a deep dish. So the conclusions. Always use a feed that with documented performance, so you know what you get. Do not change a good feed design if you don't know how to simulate or get, because that's a non-windshield situation. And there is no perfect match. Set your goal, what do you want to achieve? Use the G over T, it's a powerful way to optimize your system for RX performance. And remember, it's more easy to start at the right position from the start and do the right things rather than do things over and over and over again. That's to spend your time in a better way. And you can gain dBs by doing the correct optimization. And every tenth of a dB is valuable for EME communication. So the tools that we have been discussing here is the feed GT, EME calc, and also there are 2 plots appended to this presentation. So thank you to Senek and the EME team, the team here, and for making this possible. And also I would like to thank the people that have supported me in writing this paper. Thank you very much. And now open for questions.
I guess we should ask Paul first if he has any comments.
Dick had a question here, I think.
Any questions, please?
Dick, do you have a question?
The microphone is coming.
Thank you, sir. I once promoted the way to check your illumination optimization by pointing your dish towards the sun or another noise source, and take a plate and move around the edge of your dish and see if there are variations in the noise measurements. This way you can see if the feed is looking over the edge or not. And then if it's under-illuminating, it's more difficult. And I once promoted to move your feed, but I was not intending to keep it out of the focus point. But it's a way to, if you move it backwards, how long does it take before the dish is looking over the edge or not? But my question is, because it's all very practical and it's a bit kitchen table technology, but do you have another way to find out what is the optimum illumination? Thank you. And thank you for your very interesting presentation.
Well, the optimum, you know, by having a feed that has documented performance, you know what, that's the way, and you move the feed back and forth to find the optimum focal point together with the face center of the feed. So that's the way to do it. I know of no way to moving the feed not illuminating in different way. It's the angle you have from the feed to the dish edge. And the feed GT curve says it all. You get the answer there. Any other questions? Charlie? Yes.
I've always been fascinated by the plots where it has this big disclaimer printed on. And the disclaimer is real world efficiency may be at least 15 percentage points lower than the prediction. Is there any feeling for whether that's likely to be a bigger error with a deeper F over D dish, or, you know, it seems to, I mean, 80% down to 65 or 60 down to 45 is a big drop. So how much can you believe the efficiency curve, I guess, is the bottom line of the question.
Yeah, I guess that the absolute level of the efficiency curve, that claim, but where it is situated, it's, I guess Paul should answer this question, as he has done the analysis and these plots. But I think that also practically, from experience, you have seen that you go from these 70-80% efficiency, and if you have a 65% measured efficiency, you're good. Yeah, so that's it. I think it's from practical experience you have seen this. Oh, thank you very much. Oh, Al. I guess that optimizing on sun noise you can do on all the bands. Moon noise you only have on few bands. And optimizing on 2 dB or whatever, 1 dB, that's a hard task. But if you have 10, 15, 20 dB of sun noise, you can have a finer scale and you see the optimization in a much easier way, I believe. But they follow each other, so if you optimize on one, you get the other one. Thank you very much.
Yeah, we move on finally to Zdenek's traveler's stories about 24 gigahertz portable EME. And yeah, I just hand the microphone straight to you. And if you run over time, you are the organizer. It's all on you, boy.
Okay, thanks very much, Jan. And again, I wish you a very nice day. I have prepared for you the presentation about the 24 gigahertz portable EME. Inspiration was the trip of Rex, VK7MO, through Australia. And if I saw his activity, I said, okay, if Rex in his edge can to do that, in my edge, which is 10 years less, I have to do that too, but in the Europe. So what was the main point? First of all, the question why 24 gigahertz portable, then what to use, how to use, and the technology which I have for the EME portable, which I have extended as a 7-band for moon bouncing expeditions. Just only the portable traffic can to increase the activity on the band, because if we don't have any expedition, all microwave bands over the 23 gigs are dead. Just only on a 10 gigahertz we have a couple of the active stations. Then opportunity to offer the other friends in the world to work with the new DXCC. Activation of new worldwide locators, and it is also very great technical and moral challenge to operate this activity somewhere outside of your laboratory and outside of your home. Which type of the transverter I am using? I have in my portable setup, I am using DB6NT transverter. It's very nice made. It's very rigid, very compact. Receiver has a 4 dB noise figure. The transmitter is giving 2.6 watt, so it was easy to follow up with the power extension. Very big problem from the beginning was solid-state power amplifier. I decided the minimum is a 20 watt, which I need. DB6NT amplifiers were not more available on the market because Michael produced the 10 pieces, and all those 10 pieces are already in use between another hams. Mitsuo J1 Whiskey Queen Fox offered to help, and then it was necessary to build and do some other things about to have the SSPA in the design, which you can see here in the picture. In the beginning, on my first 24 gig moon bouncing expedition, I was using just only 7 or 8 watt output, and it was not enough. You will see why. So that first of all was necessary to build the good quality power supply for the powering of the SSPA. It's required 6 volt 20 amps and minus 5 volts. And the most important thing is that minus 5 volts has to be all the time available on the gates of TGA semiconductors. If not, you will damage the transistor with the overcurrent. So I made the 2 PCBs, each of them for one part of the SSPA. So this is the part for 10 watt, and this is for another 10 watts, which is combined together. There is also the power supply, which is supporting the negative voltage for a TGA 4915. And idle current for the TGI has to be set up for 4 amps. It's a 6 volt 4 amps. If you don't have the 4 amps, forget that the amplifier is amplifying. It's dead. It doesn't work. I was with Mirek in his lab, and one amplifier was working and one not, and we were looking why and why and why. I was cleaning, I was testing, and when I turned a little bit with this trimmer in the power supply and decrease the negative voltage and increase the current over the 4 amps, immediately amplifier start to amplifying. So, very important part, it has to be good made, and it has to be able to give you minimally 25 up to 50 milliamperes without any dropping down, and keep the open the transistors. How looks the design, which is used by JA1 Whiskey Queen Fox, and which was designed by JA8 Charlie Mike Yankee, which, sorry to say, a year ago passed away. So the design is that it's a combined two independent stages, each of them including 2 independent TGA 4915. Each of them is giving, on my side, 6 watts, not 6.8, because Toshio is a little bit higher risk guy. He's using 7 volts on the volt drain. I'm using just only 6.7 volts. So I am a little bit down so that I don't have the power like this. I have on the output 11 watts here, and on the output here I have 22 watts. So this is the schematic, how is made this amplifier. Here you can see how is the inside. This is the Wilkinson divider. Here you have a 1 watt amplifier, which is giving you the driving power for a 1 TGA and 2nd TGA, and it's a combined inside here on the waveguides, and each part of this SSPA is giving 11 watts. The waveguide combiner looks like this. You have the monopoles, which are coming from this side through the aluminum wall. Then you have the outputs here combining, and here you have a 10 watts, or in my side, 11 watts. What is also very important, on the combined output, I have the minus 30 dB port where I can measure power. So it means that I made the RF detector, which is giving me the information remotely in a place where I am transmitting about the power which I have in antenna. This is how looks the SSPA built together. This is the heatsink. I am not using Peltier cooling as Toshio is using, so I have just only two amplifiers combined together, and here you have the 22 watts output. This is the 11.2 on the one side, 11.9 on the second side. Together here you can see how is the combine everything on the heatsink. Inside in the transverter, here I have a direction coupler minus 20 dB plus 10 dB attenuation, and the power meter from the Agilent. And this is the whole design with the splitter on the input. This is a 2.4 watts from the transverter, goes through attenuator, splitter 2 times of minus 4 dB, coaxial cable, the phase shift, set up the right driving power on both sides, and here on the output is this power 22.5 watts. So result after the complete tuning of the SSPA, was 11.8 dBm on the input and 43.51 dBm on the output. So the whole gain of the system is a 31 dB. There was also necessary to use a good quality LNA. In first application, I was using DB6NT. Then I got for a test, and I bought from DL3 BPC, I bought this new one amplifier, expecting that the amplifier has a really 1.1 dB noise figure and gain 30 dB. We had available two pieces. One of them is using by OK 1 Kilo India radio. One of them I have. And I have to say that if you don't have on the output here, install good isolator with the really 50 ohm impedance, really 50 ohm impedance on 24 gigs, you will have a lot of problem with the oscillation. I think that DL3 BPC is working on to change the mechanical design, but what we have found is that this is the second stage in VLNA, and after the filter has to be something what will be matching this whole preamplifier to the 50 ohm directly here in this case, because this is the reason why, according my expectation is that this open wire 50 ohm line here, and in combination with the cover, excite the oscillation inside with the second stage and made a problem. The oscillating of this amplifier I find on 18 gigahertz. So that this is the 24 gigahertz VLNA on 18 gigahertz. I had a big peak, which was a damaging noise figure on the input totally. And in the first result, comparing with the DB6NT, where I had 11.6 dB sun noise, I had suddenly only 6.8 dB sun noise. So that I was very disappointed what I have installed and looking for. And then the Ladia also find the same problem in their preamplifier. We worked together very long time and find the solution that seriously the output has to go through the very good isolator. So this is the VLNA which I have now. Another very important part of the portable setup is good quality tripod. It means something where you have 0 backslash gears for azimuth and elevation, where you have the azimuth reader, and something what is showing you that you have perfectly set up the tripod in a right level for a ground. So then you don't have any problem with the moving in antenna in a 360 degrees and a 90 degrees in elevation, and you are always pointing to the same point. So I made a design of this. This is the extension for the solar panel gear, where I have the connection to the MAP 5525 encoder. And this resolution 0.1 degrees is enough for this small setup, which I am using for 24 gigs. So how it looks on the tripod, so that you can see, this is the whole tripod, very heavy stuff. And then you have the connection part between the tripod and solar gear, and again the measuring of the leveling of this position. So here on those two pictures you can see how it looks. So this is the elevation gear. This is the azimuth gear. Again, always looking for the leveling position. Here I am using I forgot the name of the company now, inclinometer for measuring of the elevation, and for the 24 gigs, 3 centimeters and 6 centimeters. On the expedition, I am using this 180 centimeters prime focus dish made by company Andrew. And on the picture here, you can see the setup which we had in 4U1 ITU expedition, where we were QRV from 70 cents up to 24 gigs. But as I say, in that time, I had just only 8 watt on the feed. Feed horn, I have the standard prime focus feed horn with the Kumar ring. This is the twister which I'm using for the working with the stations in Australia. Because the Rex is not able to work vertical, so that I have to tune the polarization. And here you can see how looks the feed, and this is the feed in the feed point in the dish, together with transverter. Sorry. As a controlling system for the antenna, I am using OE5 JFL. Posital inclinometer, map 25 for azimuth, and some options for the high current engines, oversupply, encoder, and all those things which are necessary connect together for controlling the system in azimuth and elevation. The first portable setup tests, in that time I was using only 8 watt, was with OK1 Kilo India radio, OZ1 LPR, and then with Charlie, that time G3 WDG. So we worked it very easy, very nice QSO, no problem. Even I was using only 8 watt. In that time, OK1 Kilo India radio, with 4 meter dish, 20 watts, and Charlie with 3 meter and 10 watts. I think that's correct. So we work at those testing QSOs before my trip to the 4U1 ITU. 24 gigahertz expedition in 4U1 ITU was relatively successful, also on 24 gigs. Because I work at Kilo India Radio, Charlie, I was a Peter with the Peter OZ1 LPR, and with the Willy LX1 DB, I work at CW QSO. Even I was only with the 8 watt. I heard and decoded stations, those stations, but they didn't decode me in that time. Partly in the wrong setup of the WES-JT software, and partly thanks to my low power. Then I was repeating the expedition to Poland, and I was QRV as a SP0 VHF. That time I had a new amplifier, 23 watt output, and I was easy copy and working everybody who was on the band at that time and worked at Kilo India Radio, Peter, Franta, Charlie Alpha, Al, W5 Lua, DL7 Yankee Charlie, LX1 DBCV again. So you can see that just only the different in, let's say, 10 watts helped me to bring the new DXCC for everybody who was a QRV. What's new? I hope that you will hear my station very soon from 9 Hotel and OY9, and I will be QRV again from 70 up to 24 gigs, and looking forward to work many of you. So thank you very much for your attention, and if you have any questions. No questions. Okay, so thank you very much for your join us first part. Now some information. We have a prepared lunch But because we don't have the restaurant just only for us, I got from reception the tickets for lunch. Please go here. I will distribute you the lunch tickets. We have a lunch from now till 13:15 expected, and 13:15 until 13:30 again, please. I would like to have the group photo front of the hotel, front of the entrance to the hotel. So thanks very much. Enjoy the lunch. Hello, hello. Gentlemen, together with the lunch, you have also one beer, okay? One beer together with lunch.